Hi, hi, welcome to iitiansgateclasses. I am Vivek Sharma. I scored 192 rank in GATE 2019 Computer Science, and I will be covering algorithm in this course. So let's start with the syllabus of the course. So here, if you see in the syllabus, they have asymptotic notations, versus time complexity, space complexity calculations. So in this topic, particularly in this topic, we will be covering time complexity and space complexity calculations for a given algorithm, and we will try to compare various algorithms, and we will be able to compare various algorithms, which one is better for a given problem. Okay, so we may have multiple algorithms for a given problem, and if we are given that we have to choose the best algorithm, using this analysis, we'll be able to choose the best one. Now we have algorithm design techniques. So these are the various techniques: greedy, dynamic, divide and conquer. This will be also the part of the course. Then we have searching. Searching could be done on various data structures. It could be array, stack, queue, graph, tree. So we will be covering all kind of searching, and again we have sorting. So how array can be sorted in different way, and which one is better, which sorting algorithm is better in which scenario. We will cover that also. Then we have hashing. We will see some hash functions. Okay. Then we have graph traverse, and minimum spanning tree. This is a particular kind of tree on a given tree. What is the minimum span? Okay. Then we have shortest path. Given a graph, what is the shortest path to go from source to destination? Okay. So we will be seeing all these topics in this course. Okay. So let's started with the definition of algorithm. Definition of algorithm. Like, what is algorithm? Definition. So don't mind my writing, because I will be writing on electronics pad. So you just try to focus on my words as well as the content of the course. So mostly mathematical terms I will be writing very comfortably. There will be no issue, but writing a whole sentence on electronic pad might be difficult. Okay, don't mind my writing. So what is the definition of algorithm? So consider algorithm as steps you are going to follow, sequence of steps you are going to follow to solve a problem. For example, if you are going to add two numbers and try to store in third number, okay, how are you going to do this? The first step could be take input or given numbers. Okay, so suppose you take input first number in A and second number in B. The second step would be you will be doing some addition function, okay, A plus B, and you will try to save it in a variable C. Second step could be this one, and third one is return C. Return C. Okay, so the C will contain the sum of these two. So this is the algorithm. This is an algorithm to add two numbers. It contains three steps. First, take input of A and B, these two numbers. Second, add them or apply some addition function and return the value. So these sequence of steps, first one is this one, followed by that we have this step, then this step. This sequence of step is called algorithm. Okay, so then we will try to see like what all property we have for an algorithm. For example, in algorithm, the steps, that sequence of steps that we are going to follow, steps we are following should be finite. Should be finite. We simply can't say that, okay, we don't know how many steps we have to follow to solve the problem. No, the number of steps should be finite. Okay. Second one is it should output something, like there should be some output of the algorithm. So given an input and algo, so input can be anything. It could be some trigger point, or there might be something that sometimes in some algorithm we don't require an input also. It could be any trigger point or any start point also. Okay, so we'll have an output. Provided an algorithm and input, we'll have some output. Okay, so we will follow that sequence of steps on this input, and we'll have the output which solves the problem. Okay, second and the third thing is, which is the most important thing, algorithm should be language independent. Okay, it doesn't matter which language you choose to implement algorithm, or which compiler. It could be Java. It could be Java. Okay, it could be Python. It could be C++, Ruby. Okay, it could be any language you follow, or any compiler, because for each language we have compiler. Okay, which takes the given steps and try to decode them into machine language. Okay, or algo should be machine independent. This is the most important thing, right? So these are the property of the algorithm, basic property of the algorithm. Right now I'm just giving you the basic introduction to the algorithm. Later on, like going forward, I'll be doing some analysis steps also. So today we will try to convert the asymptotic notation, time complexity, and such things, and you will have some understanding about the time complexity, like what is time complexity and what is algorithm. Okay, so let's see some things today. For example, see, there are various analyses given an algorithm. There could be two types of analysis we can do. Okay, there could be two types of analysis we can do. The first one could be relative, which is called relative analysis. Okay, this is also called a posteriori. Okay, and another one is a priori. PRIORI, or you can call it absolute also. Absolute analysis. So there are two types of analysis. First one is relative or a posteriori. The second one is a priori or absolute. Okay. So this thing depends upon, this relative analysis depends upon, let me change the color of this pad. Yeah. So this thing depends upon language or compiler or system processor, number of cores, like number of cores you have, the language that you are following, language. Okay, so as you know that Java runs on virtual machine, okay, JVM, Java virtual machine. So it may take more time compared to C++. There are benefits of virtual machine. Okay, you have machine independent code there, right? But the same code, if you run the same algorithm, you run on C++, not same code, same algorithm you run on C++, it may take less time. Okay, on Java it may take 10 seconds. No, C++ it could take 1 second. That is totally dependent on compiler. So that kind of analysis is called relative or a posteriori, right? And the second here it's language or core independent. Core, number of cores. Cores means CPU cores. Like in nowadays we have 8 to 16 cores on mobile or computer. So this is core language independent. Okay, core independent and language independent. Right, this one is like here the credit goes to these two, number of cores and language. And in the a priori or a posteriori, we have the exact analysis, like exact time complexity, time taken, exact time taken in millisecond or microseconds. You will have exact time, how much time your language or your cores are taking to solve that algorithm, whichever you have developed. Here it's totally algorithm dependent. Your code that you have written, your code or algorithm that you have written, it does not depend upon your course or language. Okay. So given any algorithm, if you increase the input size, increase the number of iteration or input size, sometimes it becomes, or you can say almost all the times it becomes core and language independent, right? If your algorithm is not good, it's not optimal, it may take 1 hour or 2 hours, right, to run a very simple algorithm. It does not depend upon the core also. So that's why the GATE syllabus mostly covers this kind of analysis, a priori or absolute analysis. So we will be covering this one and we won't be covering this one. Relative or a posteriori is not part of algorithm course. Okay. And here we will take lose time analysis into consideration. Right? You will see later on what is lose time analysis. We won't be taking the exact microsecond or millisecond taken into account, right? Okay. So let me give you some example of this relative analysis. Okay, so let's have some example of absolute analysis or a priori analysis. Now, suppose you have a function, okay, function, where you are passing two values, a and b, and you are just multiplying those two values, like c equal to a multiplied by b, and you are return c. Okay, so this is your function where you are multiplying these two input and returning the value. Okay, so how much time will it take? Like in case of a absolute analysis or a priori analysis, which is the main analysis we are going to do in the GATE course, that is the only analysis GATE will ask to you. Here, this is called constant time. Constant time. Okay. The multiplication depends upon the CPU, but it takes only one step. There is no iteration, there is no loop, there is nothing. Okay, it's just multiplying two numbers and returning that. So it's actually taking only two steps, not more than two steps, right? So it's called constant time. Constant time is also denoted as big O of 1. Big O of 1. This is denoted like this, constant time. This is the minimum time. Minimum time in sense of absolute analysis. Okay, in sense of absolute analysis, this is the minimum time a machine can take. Okay, now let's move on to some other example where we are having a loop. loop. For example, for here I, you all must have written a loop something like this. I equal to 1, I less than equal to n, I plus plus. Now the n is a variable whose value varies. It could vary, it could be 0, it could be 1 billion, 200 billion, we don't know. Okay, so we assume that the n value is 2 hues. It's just 2 hues. It could be any value. Okay. So right now what we are doing, we are just adding some values, x equal to y plus z in this loop. So how many times this runs in term of n? It runs n number of times. N number of times it's running, right? So if it's running n number of times, it means that here the time complexity denoted for this whole code is order of n, right? It's not constant. It is order of n. Okay. And in actual, if you try to calculate like how many times this code is running, actually it's running n plus 1 time. Okay. So see, initially I value is 1, I value is 1. Okay. Then it goes inside the loop, like how many times this statement is running, how many times this statement is running. Exactly this statement is running how many times, for loop. I will set to 1. It will check that I is less than equal to n. Suppose n is 100. It checks that 1 is less than equal to 100. The condition is satisfied. We'll go inside the loop. Okay. Then the value of I will be increased. Again, this will be increased, right? So if somebody asks you at the end of this loop, what is the value of I? Or at the end of this loop, how many times the for will run, or this condition will be checked at the end of this loop, how many times this condition is checked, or what is the value of I? It is actually n plus 1, because the I value will increase 1 by 1, 1 by 1, 1 by 1, and this condition will fail when I equal to n plus 1. So n plus 1 will not be less than equal to n, and this loop will fail. So at the end of this loop, the I value will be n plus 1. It's simple, right? So we can say that the for loop run n plus 1 time. This line will run only n times, but that this condition has been checked n plus 1 times, n plus 1 times. Okay, this condition has been checked n plus 1 times, and at the end of the loop, the I value will be n plus 1, but the order is order of n. I will tell you how it's not order of n plus 1, but it's order of n. Okay, I'll tell you in later steps. Actually, order of n plus 1 is equivalent to order of n, right? If n value is too large, we can drop this one. Okay, so later on I will be solving polynomial equation also. In case of polynomial, I will also tell you what is the time complexity. Okay, so let's move on to the next example. Here what's happening, we are running two for loops. One is simple for loop like the previous one, I equal to 1, I less than equal to n, I plus plus. Okay, and in this loop we are saying x equal to y plus z. Some step is there, right? And we have one more loop. Just after this loop has ended here. We have one more loop where we are saying that there is one variable p equal to 1, p is less than equal to n, p plus plus, for k equal to 1, inside this for loop, we have one more for loop. K is less than equal to n, k plus plus. And here we are performing some other operation like a equal to b plus c, right? So inside this for loop, we have one more for loop. Okay, now let's do some analysis on it. If somebody asks you what is the total time complexity of these two for loops, where one is basically a for loop inside another for loop, this whole thing is inner for loop. There is one for loop is inside another for loop, okay, and this is the separate for loop, right? We already have seen that it runs n plus 1 times. Okay, now we have to check how many times these two for loops runs, one for loop inside another. Okay, so when p is equal to 1, how many times this for loop is running? When p is equal to 1, how many times is this for loop is running? It's actually running n plus 1 times. Okay, when p is equal to 2, how many times this for loop is running again? N plus 1. And we have already seen that in case of n plus 1, we are denoting it as n. So you can say n. That's why I told you that this analysis, this absolute analysis, is also considered as loose analysis. Okay, it's not very strict. We are not going for the exact value. We are going for like something approximate value. When the value of n increases, we can drop the other constants like this. N plus 1 can be considered as n. Okay, so when p equal to 3, again it will run n times. Till p equal to n, it will run n times. Okay, so for 1 it runs n times, for 2 it runs n times. So this whole loop, this inner loop have run n square times, n multiplied by n square times. Okay, so what will be the time complexity here? What is the time complexity here? It's actually, if you see n for this, n square for this. So let me write it here. It's n square plus n. Okay, n square plus n. So somebody can add one here, or somebody can say n square plus 1, sorry, n plus 1 square plus n plus 1, something like this. So we are taking approximate value, so we can say that it's n square plus n, right? So in terms of order, or in terms of big O, what we can say, it's actually n square only. It's not order of n square plus n. And order of n square plus n is actually same as order of n square. Because when we have two functions like this one and this one, we will consider only the bigger function in case of order. As the value of n rises, as the value of n increases, right, the importance of n decreases compared to n square, right? So that's why order of n square plus n is equivalent to order of n square. Okay, so let me give you one more example. What if we have for loops like this? Okay, we have a huge program where we have calculated the first for loop or first while loop, it's running n square times. Then we have 3 inner loops, a loop inside another loop, and there's another loop inside that one. So we have 3 levels of inline loops, right? So it's order of n cube. If you have n square plus n cube, plus there's like 4 level of loops are there, n4. Then we again have 2 levels of n square. Okay, so now if you see there's one polynomial equation like this, n square plus n cube plus n4 plus n square. So now time complexity will be considered as order of n raised to power 4 only. we can drop the other values. Okay, we can drop these values and we can only focus on the largest, you can say, polynomial entity, which is order of n4. Order of n4. So now the time complexity will be order of n4. This much time it will take. We will be dropping these values. Like in the previous example, we have order of n in this loop and order of n square here. So all over time complexity is order of n square. I hope this is clear. Okay, now let's move on to the next topic. Next example, actually. I want to make it very clear, so I'll be moving to next example also until it's clear. Okay, so now let's see one while loop. Let's compare two while loop actually. Look carefully here. I initializes I to 1. Then I say that until I is less than n, suppose n is a very huge number, I equal to I plus 1. I'm running one while loop here. Okay, and I'm comparing this one to this. I'm saying that I is equal, initially is 1, I is less than equal to n, and I'm saying I equal to I plus 2. Okay, so suppose if value of n is equal to 100, how many times this loop will run? How many times? It will run 100 times, right? Actually, this condition will run more than 100, 101 times, 101. Okay, but this condition will run 100 times, 100 times. And how many times this will run? This for loop will run. Okay, so IE value will go from 1 to 3, and then 3 to 5, then 5 to 7. So we are actually going, we are only checking odd values. We are moving from one odd value to another odd value. Even values are absent. Okay, so basically we are checking only half of the number out of 100. So it will run 50 times. It will run only 50 times. Okay, so this is half. Just by adding 2 here, the time complexity reduces by half. So here the time complexity is order of n, and here the time complexity is order of n by 2. Okay, n by 2, because only half of the steps will be executed. Exactly half, right? So order of n by 2. Now, as I already told you, that the effect of constant won't be considered. Effect of constant won't be considered in this absolute time analysis. Order of n by 2 is equivalent to order of n. This 2 can be dropped. Similarly, if we say order of 2n, it's similar to order of n. Okay, so this is a very good example. Now, what if I have added 10 here instead of 2? Let me erase it. What if I have added 10 here? I equal to I plus 10. Then how many steps did we have executed? In that case, from I equal to 1, we simply jump to 11, then to 21, then 101. There. Okay, 21 to 31, then 41, 51, 61, and till 101. So we will have executed only 10 steps, which is basically 100 divided by 10. So in that case, our time complexity would have been order of n by 10. This is also equivalent to order of n, because the effect of constant can be negligible, can be considered as negligible in absolute analysis. Okay, it could be 100, it could be like order of n by 100 is also equivalent to order of n. Okay, I hope this is clear. Then let's move on to some more complex example. Now instead of adding values, we will multiply. Like we say, while initially I is 1, I is less than equal to n, we say I equal to 2 multiplied by I. Now what will happen? Now value of I increases exponentially. We are not adding 2. We are at each step, we are increasing the value of I, and we are doubling it. Okay. So initially value of I is 1. Then in the next step, it will be 2. Then it will be 4. Then it will be 8. Then 16. Then 32. Then 64. Okay. Then 128 directly. So within very few steps, like within like 1, 2, 3, 4, 5, 6, 7, within 7 steps, we have gone out of this loop here within 7 steps. So how can we calculate time complexity when we are multiplying the value of I with 2? How can we calculate it? Okay, let's calculate it step by step. So at the initial step, the value of I is basically 1, which can be written as 2 raised to power 0. Then it can be 2, which can be written as 2 raised to power 1. Then 4, we are doubling value, right? So 2 to 4, 2 raised to power 2. Then 4 to 8, 2 raised to power 3. 8 to 16, 2 raised to power 4. Okay, then 32, 2 raised to power 2 raised to power 5, right? So suppose if value of n is we don't know, some very huge value, right? So how many steps would have it taken? How many steps? We are more interested into number of times this loop have run, and that is the time complexity. Number of times this loop have run. That is the actually approximate time this loop have taken, right? Suppose it have taken k number of steps. So at the end of kth step, the value of I would have been 2 raised to power k, and which will be actually either equal or greater to n. So let's consider the worst scenario, which is equal. So if we have run this loop k number of times, if we have run this loop k times, the value of I will be 2 raised to power k, right? Like this, from 1 to 2, 2 to 4, 4 to 8, and like this. Okay, so it will be 2 raised to power k. And when we break this loop, it would have been greater than equal to n. Okay, let's take the equal scenario, 2 raised to power k equal to n. It could be greater also, but let's take the equal scenario. Equal. Now what is the number of steps? Minimum step. We say that let's take log both side. Okay, and we all know that we in the logarithmic operations, if something is like this, we can write it like k log base 2. Here the base is 2. We can write it like this. Okay, this term can be written like this. This k can go before this log, and the value of this is equal to 1. We know that log of a is equal to 1. Okay, where base is same to this value, then it's 1. Okay, so this value can be written as k equal to log base 2n, log base 2n. Okay, let me erase it again and let me tell you again. Here, if we have run this algorithm k number of steps, the value of I would have been k, and it has been greater than equal to n, then only this loop will break. Then if we take log both sides, log 2 raised to power k greater than equal to log n, we can take equal scenario also, then log base 2. Okay, this will be k greater than equal to log n. So it would have been taken these many steps only, log base 2 n steps. That's it. So the time complexity would be order of log base 2 n. This is the time complexity when we multiply I with 2. So let's move on to the next example. Here, you say that initially, okay, here you are not taking I. You are saying that we have passed some value n, which is a variable. And this loop will run until the value of n is greater than 1. And at each step, I am dividing the n by 2. Then what is the time complexity? It is the same time complexity as the previous one, but in a different manner, you can calculate it. So what I'm trying to explain here is, how can you calculate time complexity when you have given various scenarios, various algorithms? Like, okay, so the previous step, you don't have to mug it up, right? That whenever I am multiplying I with 2, the time complexity will be order of log n. And when I'm dividing n by 2, the time complexity is again order of log base 2n. You don't have to mug it up. I'm going to explain it to you. Suppose initially the value of n is 32. Okay, the value of n is 32. Then at the first step, the loop will continue because 32 is greater than 1. Okay, at the first step. Then we divide it by 2, 16, again is greater than 1. Then we divide it by 2, 8 is greater than 1. Again, 4 is greater than 1. Then we again divide it by 2, 2 is greater than 1. Then again, when we divide it by 2, 1 is not greater than 1, and the loop will break. But how many steps we have taken? How many steps? Suppose we have taken k number of steps. Okay, if we have taken k number of steps. So at each step, what's happening? Let me explain it to you. At each step, the value of n is decreasing by half. Okay, the value of n is decreasing by half. So initially, I will do analysis here. Initially, the value of n is n, then it's n by 2, then it's n by 2 raised to power 2. Okay, this is the first step, this is second step, this is third step. Okay, if we have run the algorithm k number of steps till it reaches 1, okay, or less than 1, then at the kth step, the value of n will remain n by 2 raised to power k, which is basically we are saying that less than equal to 1. And at this position, at the kth step, the loop breaks and we break out this loop. Okay, so the k is basically time complexity. K will be the time complexity because we have run the loop k number of times. So we have to calculate k. So let's calculate k. N is less than equal to, 2 raised to power k. Now let's take log both sides. It's again the same thing. 2 raised to power k greater than equal to log n log 2. Okay, so k is greater than equal to log n. So time complexity would have been log base 2 n. Okay, it's the same thing. So this is how we can calculate time complexity for any given, you can say code snippet, any given code snippet. So you have seen these kind of code snippet when we have I equal to I plus 1, time complexity is order of n, I equal to I plus 10, or I equal to I plus 100, or anything, I plus 100, anything. The time complexity is order of n again. When we multiply I with 2, it becomes log n. When we divide n by 2, each time we decreases by 2. What if here we have 3, n equal to n by 3? Then these steps will run like this: n by 3, n by 3 square. At kth step will be n upon 3 raised to power k. So time complexity would have become, once we taken the log, we won't take log base 2, we will take log base 3. So time complexity will become log base 3n, log base 3n. Okay, simple, it's simple. And then let's move on to the next kind of example. Here, if you see, we say I equal to 2 initially, and I is less than n. We will run the loop until I is less than n. And each step we will square the value of I. Now we are not multiplying with 2, we are squaring the value of I. We will be squaring the value of I. Okay, so let's take an example. Like if the value of n is basically 1024 or something like this, how many steps would have it taken? Initially the value of I is 2, then it will become 4, then 16, then 256, then 256 square, which is obviously greater than 1024. These many steps. Previously it have taken exactly 7 steps, now only 4 steps. This is the first step actually. This is the first time we are entering in the loop, only 4 steps. Okay, so how can we calculate a time complexity if n value is very huge, like very huge, very large? How many steps? You must have some function. So how can we calculate the function? Okay, 2 can be written as 2 raised to power 0. 4 can be written as 2 raised to power 2. 16 can be written as 2 raised to power 3. 256 can be written as 2 raised to power 4. Okay, so at the kth step, the value of I where the loop breaks would be at the kth step. It would be 2 raised to power k. Okay, 2 raised to power k, which is basically greater than or equal to n, which breaks the loop. Now let's take log both sides. Again, let's take log both sides. Log base 2 to raised to power k greater than or equal to log n. So this will convert into the 2 raised to power k will go here, and log 2 will become 1. Right, let me write it here. So log base 2 raised to power k will become 2 raised to power k log 2. This will be 1. Okay, this is 1. This whole thing is 1. So now we can say 2 raised to power k is greater than or equal to log 2n. Now what is the value of k here? Again, let's take log both sides. Again, if we take log both sides, it will become log 2 raised to power k greater than or equal to log 2n. Okay, and this will become 1. So k is greater than or equal to log n, and the base is 2. So the time complexity is not log n, but log n. Whenever we have the power as per this calculation, it will become order of log n. Okay. For more understanding, let me take one more example where I will change the initialization value and the power. So initially, if I value is 2, while I is less than n, I equal to I raised to power 20, how much time will it take? right? Now the I value will increase like this. Initially it is 2, which is 20 power 0, okay, equal to 2. Then the next step, it will become 2 raised to power 20 power 1. Its next step, it will become 2 raised to power 20 power 2. In the next step, it will become 2 raised to power 20 power 3, until the kth step when loop breaks, 2 raised to power 20 power k, which is greater than equal to n. Okay, I value will become like this at the kth step. Okay, so the k is time complexity. Let's calculate k. Let's take log base 2 both sides first. We have to take log base 2 to solve this. Okay, so this will cancel, or you can say this will move here and this will cancel. So it will become 20 power k log base 2 n. Now we have to take log base 20, not 2, 20. Then this will be solved. So k greater than equal to log base 20 log base 2 n. Now can you see the relation? Here the inner log, this one, the inner log base is actually equal to the initialization of I, and the outer log, this one, is actually the power of I. So remember this relation. I have solved this using this example, but you can remember this also. You don't have to mug it up. You can remember logically. Okay. So now let's move on to the next. Some few more examples we will see. Okay. So what if I write a like 3-level for loop, like for I equal to 1, I'm running it to n, till n. Okay. So you can write it like I equal to 1, I is less than equal to n, I equal to I plus plus, something like this. Okay. Okay. You can run it like this also. And inside it, we have something like j equal to n initially, and it's running from n to 1, not 1 to n, it's running n to 1. J is greater than equal to 1. J equal to j divided by 200. So at each step, we are dividing the value of j by 200. Okay. Now there's one more loop inside it. For k equal to 2, k is less than equal to n raised to power 5, k equal to k cube, and I'm say x equal to y plus z. You see this for loop. This is this for loop. So these are the nested for loop at 3 levels. These are nested for loop. Okay. Now let's look on these for loops one by one. Let's look only at this for loop. How many times what do you think this for loop will run? Okay, this for loop will run. Obviously, we are doing k raised to power 3. In the previous example, you have seen that we have done I raised to power 20. Here we are doing k raised to power 3. Okay, so it will be the power will be outside, right? 20. It will be log 3 outside, and the initialization 2 is out inside, and then we are running it till n raised to power 5. So this is the time complexity if we run this loop one time. If we start it from 2 and go till n raised to power 5, and each time we increase the power by 3. If we run this loop one time, initialization from 2 to and we go to n raised to power 5, this will take this much time. Okay. So again, let's go to the previous example. Here the initialization will come at the inner log and the power will come outer log. Similarly, you can say the initialization will come to the inner log and the power will come to outer log. Okay, so we have checked this for loop. Now let's check this one. How much time do you think this will take? Okay, this will take log of 200 n. Okay, let's go back. This example. Here we have divided n by 3. Okay, and we are going from n to 1. We have divided n by 3. And the time complexity is log base 3 n. So here we are dividing j, and j is going from n to 1. J is divided at each step by 200. So this will take log of n. But if we are running these steps log 200 n times at each step, at first step, it's taking this much time. At second step, again, this is taking this much time. At log 200 n time, it's taking this much time. So we have to multiply these two. Till now, we have considered only these loops. Okay. Till now, we have considered only these loops. Now let's take the outer loop also. The outer loop is taking order of n only. So it's n multiplied by log 200 n log n 5. So the time complexity is n multiplied by log n multiplied by log n. And you can mention the base also. Here base is 2, here base is 3, here base is 200. So nobody will ask you more complex question compared to this one. Okay, this could be the most complex question to be asked for a given code snippet. What is the time complexity with given basis? Okay, this is how you can solve it. Now let's move on to one tricky question here. Now there is one for loop I equal to 1, I is less than equal to n, I plus plus. I equal to 1, I is less than equal to n square, I plus plus. I equal to 1, I is less than equal to n cube, I plus plus. So we have nesting at 3, we have nesting of 3 levels. Now if you see, a general student will solve it like this. This is running n cube times, this is running n squared times, this is running n times. So our time complexity is n multiplied by n squared multiplied by n cube, which is equal to n raised to power 6, and which is wrong. How? Let me tell you. Initially, the value of I is 1, and it checks that, okay, 1 is less than equal to n. Condition is satisfied. Let's go inside the inner loop. It again sets value of I to 1. The same variable. It's not j or k or p or q. It's the same variable. Now value of I is 1 here again. Okay. So it checks that, okay, 1 is less than equal to n squared. Let's go inside. Again, it's setting the same variable. It checks 1 is less than equal to n cube. Let's go inside and do some x equal to y plus z or whatever. Now questions. But This loop will run n cube times. So at the end of this loop, the value of I will be n cube plus 1. So once it go back here and it check the condition, before checking the condition, it will increase the value of I, sorry. So it go back here and increase the value of I by 1. It will become n cube plus 2. And then it check the condition. N cube plus 2 is basically greater than n square. So it won't enter again. So it go back here again. It will increase the value of I. So it will be n cube plus 3. N cube plus 3 is greater than or equal to n. So the whole loop will run only n cube plus 3 times, or order of n cube only. If somebody asks you very specific number of steps, you will tell that at the end of all the loops, the value of I is n cube plus 3. In the gate, they may ask you very specific value of I. At the end of these all 3 for loop, what is the value of I? You can't say n raised to power 6. It's n cube plus 3. And the time complexity for all these 3 nested loop is order of n cube. It's not order of n6. Okay, remember this. This is a very good example. Okay, so that's it from today. And in the next class, we will be covering asymptotic notations. Okay, this is very important topic. And some part of like recursion also. Recursion, like what is recursion? How can we calculate time complexity of recursion? What is recursive function? Recursion and recursive function. Okay, so we'll be covering these 2 topics in the next class. Thank you.